Well, I think we're going to go ahead and get started. We're at 5:59 and seconds away, so it looks like we have a nice quorum. So let me introduce myself. My name is Erin Deely, and I'm the Director of Recruitment for the College of Science. I get to work with the next gen scientists and their families, and also I get to do a lot with science outreach, and hence my role with the Science Café series. For those of you joining us for the first time, welcome. Those of you that joined us for our talk last week with Joost van Haren, welcome back. And many of you may have attended or participated in one of 5 formerly and then recently 4 venues around town where we host Science Café talks at different venues. So this was our effort to kind of salvage some of those planned talks for this spring. So we basically borrowed a few speakers from the different venues. So last week's talk was from our Tucson Botanical Science Cafe, and this week we have our speaker that was scheduled to speak at Magpies or Downtown Science Cafe, and next week it'll be the Saddlebrook speaker, and we'll introduce, tell you about that talk next week, which will wrap up this 3-part series. And so these are being recorded, and as I mentioned to the folks that were in for earlier, we will be putting this on our YouTube channel, and that link will be made available on the College of Science website. So you can visit that at science.arizona.edu. And there's a tab at the top that says community, and there's a Science Cafe link. And so you can find information there. I also want to mention, we're going to have I'll give you the format. I'll introduce our speaker. He'll give the presentation, and then we'll do question and answer, live with him at the end of the presentation. However, I'll be moderating the questions that are coming in during the talk. So if you have a question while he's speaking, simply go to the bottom of your screen. There's the Q&A function, and you can submit your questions there. And then I'll share those with Ariel at the end, and we'll address as many of those as possible. And depending on how many questions, we usually allot about a 15-minute period. And then we'll conclude the session. With that, let me go ahead then and introduce our speaker. And he shared some great information about himself, both professionally and personally. We'd like to remind everyone that it is a culture at the College of Science and the University of Arizona. We're a state school, so we like to share the science that's being conducted, not only for higher ed purposes, but for our community, that everyone can take advantage and incorporate this into their daily lives and inform folks. And so we always have great scientists that are willing to share their science. So, we're very grateful for you coming and speaking with us tonight. And with that, our featured researcher, Ariel Leger, earned his bachelor's degree from the University of, from Quest University, Canada, and lived in British Columbia for a decade, working in forestry and sustainable agriculture. He is seeking his master's degree. He's soon to finish. It sounds like July, August time period of this year, woohoo, in the Department of Environmental Science at the University of Arizona. And he researches soil health and sustainable agriculture in arid environments, specifically organic matter in soil, to answer the questions, how do we increase food security in the face of climate change? He explores how people steward landscapes in ways that increase soil organic matter. You'll hear SOM quite a bit today, I believe, in the talk, to restore degraded landscapes and provide for the needs of people in society. And some personal notes. He is spending quarantine helping folks with food-related mutual aid and rent relief. So you can hit him up if you want to get involved, and we can take that in the Q&A. We're happy to share out that information. He plays accordion in a klezmer band and likes to celebrate Jewish holidays with music and community. And like many of us in the Southwest, he likes to get outdoors whenever he can to camp, hike, climb, and look for edible plants and mushrooms. It is my absolute pleasure to welcome Ariel Leger for his talk, From Invasive Shrubs to Grassland Restoration, the Chop and Drop Method.
Thank you so much, Erin, for that lovely introduction and the introduction to myself, but also the college. And I think that it's also lovely as a land-grant university to acknowledge the people who have been stewarding this land for millennia and keep stewarding it, and that we're on the traditional territory of the Tohono O'odham Nation right now, and the people of the Pasquayaki tribe as well. And I am going to be sharing today my research about the grasslands in this area. So this is a picture from one of the areas that I have been studying. It's a picture that was taken during monsoon season. You can see a coyote there on the right. And there is a pile of branches on the left, and that is a mulch pile that I laid down there. And these arid grasslands are lands that I've really come to love and enjoy spending time in. They're also really important for communities in Southern Arizona, communities who depend on these grasslands for their livelihood. Unfortunately, a lot of these grasslands are currently degraded. So the picture on the bottom left, is a picture of the same grassland area, but a specifically degraded part of it. They naturally have sort of bare and open patches, but these patches are increasing as we're seeing plant communities shift and climate shift as well. And my research is focused on how to use amendments like the mulch pile that we see here and the one that I showed earlier on to increase the health of the soil and also sort of restore the ecosystem as a whole. So once again, my name is Ariel Leger, and I'm going to talk to you about enhancing rangeland soil and plant health using compost and mesquite mulch. So the outline of my presentation is really going to be a three-parter. I'm going to start by introducing the grasslands with a little bit more depth, arid regions in general, and I'm going to talk about that process of degradation. What is leading these stable grasslands to shift into more unstable, more open areas with more bare ground, what the consequences of that are. Then I'm going to really link that into that process of degradation into soil health. So talking about specific measurable soil properties and the ecosystem processes that depend on those soil properties. And finally, I'm going to tie that together with my experiment, my case study using mulch and compost to really impact those soil properties and processes and restore, bring back health to the ecosystem as a whole. So the grasslands that we live in Southern Arizona are semi-arid or arid grasslands, and grasslands like these and drylands in general are vast. They cover 41% of our planet, and they support over 2 billion people. Those areas are growing as the planet gets drier and warmer, and these grasslands, which are already fragile, are degrading at a really high rate. Already, a full quarter of areas that are considered drylands are in some sort of state of degradation. What that means is that some of those soil-based ecosystem processes aren't functioning correctly to support the vegetation and the animals in this area. And if we want to bring back health to these degraded areas, we really have to hone in on restoring the sort of cycles, those processes that are happening in the soil. So processes like the cycling of nutrients that plants depend on, the cycling of water, those hydrological processes that plants and animals also depend on, and also soil stability. So holding soil itself in place is something that's fairly complicated and relies on a whole process that the ecosystem carries out in perpetuity. So if we want to restore the health of that ecosystem, we really have to focus on restoring the wholeness, if you will, of those cycles. Because without them, whatever we try to change is just going to slide back into degradation. So we know that mulch and compost can help do this, and I'm going to tell you how. But before I do, or sort of to give context to that, we have to know a little bit about the ecosystem itself. So this picture right here, this diagram, is a sort of cartoon version of a grassland in Southern Arizona. And we can see that there is a mesquite tree that I put here and a few bunch grasses. And the box around these plants is meant to represent the above ground portion of the ecosystem. This above ground portion is controlled in a really important way by rain and the available precipitation to this ecosystem. And it'll change a little bit, but if it's in a stable state, it'll be, you know, about 5 or 10% mesquite at the utmost, and the rest will be grass cover, and what isn't covered with grass, there'll be some shrubs or some forbs, a few little things, but it's kind of steady in that state. Now I'm going to come back to that idea of this ecosystem being in a steady state several times throughout this presentation. Another part that we have to understand is that there's a whole below ground section to this ecosystem that's helping support that above ground portion that we see. Below ground, we don't have trees and grasses, but we have roots and plant litter that are down there. And we have, just as above ground, there will be animals and birds that are helping cycle nutrients and eating plants and dying and depositing nutrients here. Below ground, we have a similar ecosystem. So we'll have microbes like bacteria and fungi that are living in the soil, and we'll have little worms and arthropods, arthropods being a host of animals like, or insects rather, like termites and ants that play really important processes, eating that plant litter and those roots and helping it make that litter available to plants in turn. And that process of soil life, decomposing that plant matter, results in soil organic matter. So Aaron introduced soil organic matter briefly before, and that SOM here is soil organic matter. And that soil organic matter is deeply important to a lot of the ecosystem processes that I had described, and also to soil characteristics. So this above ground and below ground part of the ecosystem is regulated or controlled, if you will, by soil moisture in the same way as the above ground portion is regulated by rain. And together they're maintained in a dynamic balance by elements of disturbance. So we have grazing by cattle and wild animals, fire that periodically comes through these landscapes, and also the climate. So climate changes and shifts will kill out some plants and make the conditions more hospitable to others, and that dynamic disturbance process is keeping these ecosystems in balance. And they're doing that with those three ecosystem processes that I had mentioned before. So soil stability, nutrient cycling, and water cycling. So when these ecosystem processes are intact or are functional and natural disturbances are coming in regularly, they can maintain that dynamic balance in this ecosystem. This doesn't always happen, however, and we can end up with areas like I described before. But how does that shift happen from that grassland to a degraded area here? Well, the NRCS looks at it this way, and this is a complicated diagram that I'm going to do my best to explain, where each of these boxes represents a stable state, a stable ecosystem, and the arrows between them represent different pathways of degradation or restoration. So different ways that they shift from one state to the other. So up here on the left, we have a grass-dominated system in this green box. And you can see if you read the fine text, which you don't have to, that it'll shift a little bit between the sort of dominant plant species here. But in this ecosystem, no matter how much it shifts within those bounds, those processes are still whole, and it's maintaining that grass dominant system. There's another stable state that we have on the left, or on the right rather, of the screen, that is mesquites and natives. So there are less grasses here, more shrubs, more mesquites. It can also be a stable state. And there's a pathway of degradation from that grass-dominated system to this mesquite and native-dominated system. And we have a third stable state, which is a dense mesquite eroded one. So in this condition, there are very few grasses, mostly shrubs and mesquite and cacti, and it's similar to that picture that I had shown before. And between each, an important part of this last ecosystem is that there's a lot of bare ground here. The soil is not being held in place. That soil stability, that ecosystem process is not really functional. Between the grass dominated and the mesquite and native dominated systems, you have these disturbance elements of cattle that are still there, but no fire. So when there's no fire in the landscape, you can kind of transition from a grass dominated one to a mesquite and native dominated one. And you can also, depending on different conditions, transition from that grass-dominated ecosystem to the dense mesquite-eroded one, the one that doesn't provide us with the same ecosystem services that we're looking for, that livelihoods depend on here. And some elements of disturbance that are present there would be heavy grazing by cattle, drought, and also soil degradation. So when there isn't that soil stability or those nutrients or that water that's cycling, we can end up with that dense mesquite eroded system. The same thing can happen here on the right, from the mesquites and natives down to that dense mesquite eroded system, the same sort of processes. And I want to really highlight those boxes in red, that degraded soil element of those pathways of degradation. Those are unique to this sort of transition to this dense mesquite eroded system. And those are the elements that we want to be addressing with our restoration. So we can really see that this grassland, which is a picture that was taken in the Altar Valley, is in that stable state, that grassland dominated state. You can see that there are some mesquites in here, there's grazing that's happening, but there's a dynamic balance that's being maintained here. Further back, you can see a little bit more dense mesquite, and you can see that this landscape is not one contiguous block, but a sort of mosaic of different states of degradation or of health. And this is kind of what it looks like, or what it looked like in 2005, I believe. There was a really amazing study that was done to sort of look at that shift in dominant vegetation that can be one of those indicators of degradation. And it showed that there was a large scale shift towards woody plants and non-native grasses. So in this picture that we have on the slide, you can see that the redder colors are more woody plants, the greener colors are less woody plants, so a more grass dominated system. And anywhere that has those hashed lines indicates that there's a presence of non-native grasses. The part of this map that I'm going to be focusing on today is the Altar Valley. It was identified as a priority restoration area here because there's a high potential to bring it back to a healthy state. And just to sort of go back for a second to this process of degradation, I'm going to zoom in on the sort of arms here, these processes of degradation that we can see highlighted right now. And I'm going to really explain how those happen and how mulch and compost can intervene in those processes of degradation to bring back the ecosystem health that we're looking for. So if this is one arm, as you can see sort of down in the bottom little square, if this is one arm of degradation, one pathway of degradation, it involves hydrological, biological, and also soil related elements of degradation to it that sort of bring it from a stable state at the top to progressively more degraded stable states. So to zoom in, this is sort of known as a ball and cup model in ecological circles. And these are these two balls and cups. And so we have an ecosystem, which is represented by that ball. Let's say it's that grass dominated system that is living in this sort of cup that represents a stable state. So that ecosystem can bounce sort of back and forth a little bit. It can have a few more grasses, a few more shrubs, but it's gonna stay in general in that stable state until there's an element of degradation that happens. And one of those first ones would be drought and a climate shift. So it gets drier, it gets hotter, and that'll push that ecosystem ball from our stable cup into the next sort of lower cup, which is also a stable state, but it's more degraded. So that'll be dominated by mesquites and natives, for example. That new ecosystem is now maintained in a balance here. It can change a little bit, have a few more shrubs, a few more mesquites, maybe a little fluctuation in grasses, but in general, it's stable and it's really difficult to get it back into that previous state. So, to explain sort of how that happens step by step, we have the climate that we already talked about. And here in the Southwest, we have a climate that's getting progressively drier, progressively hotter, and progressively more erratic. And we can see that in this graph on the top. So there's this line here that represents drought line. So above it, it's wetter than normal. Below it, it's drier than normal. And we can see that in the recent past and in the projected future, it's going to get a lot drier and a lot hotter here. So that leads to that first sort of shift, that hydrological shift into a degraded state. Then you have a biological shift of a reduction in grasses. So this next sort of graph shows that as time gets drier, you see a progressive loss of perennial grasses. So here at Group 1 wet sites, this was a study that was conducted in Southern Arizona as well on a grassland that showed as a drought progressed over the years, over 12 years of drought, you saw progressive loss of grasses. So you can see a loss of grasses in the wet sites, also in those intermediary sites, and a sort of maintenance in those dry sites. And the final sort of stage of degradation is really that soil-based degradation. You lose soil. Water comes in, there are no plants. Those big sort of monsoon storms will come in, and we don't have the grasses to stabilize them. And then we see a degradation happen of those soil resources. And this is a picture of a particularly degraded area where people tried to hold back that water, but it eroded the side of this cut bank here. So that is kind of what's happening on a large scale in this area. As we see more and more woody plants, less and less grasses, we're seeing those soil resources get degraded. What I want to talk about next, so now we really understand that pathway of degradation and restoration, is those soil properties and processes that we're trying to restore in order to get back to the state that we want. So when thinking about soil properties, there are myriad soil properties that we can measure, but it's helpful to think about them as physical, chemical, and biological soil properties. So physical properties, you have things like soil texture and the surface conditions, so crusting of the soil that can happen in degraded areas. Chemical soil properties that you can measure are the content of nutrients that are available to plants and other animals as well, microbes. You can also measure things like the pH, so the acidity of the soil. And those are really important soil properties to think about when we're trying to improve the condition of an ecosystem. And there are a host of biological properties that we can measure. We can measure the amount of microbes that are around, how quickly they're eating organic matter and cycling nutrients. And all those are really important soil properties to think about that we measured in our study and that we're trying to improve in order to bring this ecosystem that has degraded soils back to a state of restoration. A useful analogy that I like to think about is the physical processes can be thought of as the lumber in the soil. So that would be, these physical properties are like the texture. So those individual properties are taken and they're brought together by chemical properties. So the different nutrients that are around and the biological properties like the microbes and animals are really using those chemical nails and screws to glue those physical properties together into what we see right here, which is a healthy soil that has a good structure. There are roots growing, and it's a good habitat for a lot of soil microbes and different soil organisms, can allow water to flow through it, roots to grow through it. So those are the soil properties that we're trying to restore to get that healthy soil. So we know that mulch and compost can both affect these soil properties in a host of ways. They can protect the soil surface from rain, reduce evaporation. They can add nutrients, help retain nutrients that are already there or cycle the nutrients. And they can increase the biological activity. So they can provide food for those microbes and other organisms that are in the soil. And those are all properties that mulch and compost are helping improve. So if we think about how those properties are linked to processes, we can use this diagram where we have sort of a circle and all of these properties are living inside this circle. They're overlapping. They're physical properties, chemical properties, biological ones, and soil organic matter, which is really important to all of them and affected by all of them. And together, these properties that are living within this circle are contributing to ecosystem processes. So you can kind of think of them as groups of properties, if you will. Those ecosystem processes that we're talking about are water cycling, nutrient cycling, and soil stability. So we really want to be able to improve these processes so that we can have a self-sustaining ecosystem. And without those, we're going to continue seeing this downward slope of degradation where these ecosystems are maintained in these stable, degraded states. So we need to improve those properties, to improve the processes, to return those ecosystems to the grassland dominated states that we want. So now finally, I'm going to talk about how we did that and how we measured it and what we found by using mulch and compost to improve those characteristics. So what we did is we saw that we can actually improve a lot of those properties by using amendments. We can improve soil organic matter, water holding capacity, plant productivity, reduce runoff, quantity and quality. And people have shown this, that mulch and compost can do this effectively in arid regions around the world. So we decided to use 2 amendments that are locally available and that can improve those properties and the ecosystem processes that we're trying to restore. So those 2 are mulch that we can see here on the left, rough mesquite branch mulch, and compost that we can see on the right. Both locally available, both really effective. So we know that mesquite is already present on these landscapes. A lot of those stable states have mesquites that are there and they're actively being removed. So we're wanting to leverage this waste wood from mesquite removal and use it as a resource for restoration because we know that it's effective. So the way that we did this and what it looks like is we applied the mulch and we applied a combination of mesquite mulch, just rough branches, and compost. So we can see that mulch on the right and the compost and mulch on the left. And we compared their effectiveness on restoring soil properties and on restoring vegetation compared to seeded and unseeded controls. We can see here in this picture in the middle, just broadcast some seed there. So these 3 pictures were taken at the beginning of the study. The green and the mulch is just leaves from that mulch that haven't fallen off yet. We did this in a replicate study design. So we did it multiple times in multiple different places to try to see if it was effective. And we measured nitrogen fluxes and microbial respiration, which are linked to nutrient cycling. We also measured soil moisture and temperature, which are linked to hydrological processes, and soil structure and vegetation, which are linked to soil stability. Our hypotheses were that we would be able to increase the soil moisture, increase the microbial activity, and increase the soil stability and vegetation. All of those things are linked to the processes that we're trying to restore. And what we found, I'm going to go through those one at a time, the hydrological processes first. What we found was that amendments were able to increase soil moisture, so that's great, but that the story was a little bit more complicated than that. We found, because we applied 2 different rates of compost, just the 3 centimeter and also a 6 centimeter layer, we found that the 3 centimeter layer was able to retain short-term a lot more moisture than that thicker layer, but that thicker layer kept the moisture around for a really long time. It took a lot longer to dry out. Another really interesting thing that we found was that the frequency of rain events and the size of them really mattered. So whether it's monsoon, heavy monsoon rains, or those short little winter rains that we get, the different amendments responded differently to those. Really interesting. So here we see that mulch and compost really improved the average soil moisture. So on the right, we have the average soil moisture. There's way more of it. On the left, the controls, there's less. And here we see that the frequency of rain effect. So we can see here in this highlighted box, all these lines are different treatments. And we can see that when a rain event happens, there's a peak and then it slowly dries off as the days go on. So on the bottom axis here, we have time, and on the vertical axis, we have the amount of moisture. So as rains happen, they let in a whole big pulse of moisture into the soil. And we can see, so this yellow line here is a little application of compost at 3 centimeters, and underneath it is mulch, and underneath that is that thick amount of compost. So we can see that both the short amount and just the mesquite branches actually keep more moisture in for longer than that thick amount of compost. So this is really useful in those short intervals between precipitation events. We also saw that during larger storms, that difference wasn't as big. So if there's enough water that gets in the soil, we can really see here that thick application of mulch gets a lot of water and holds it in for much longer than the other treatments. Smaller storms, you see the opposite effect. So this bottom line here is really not keeping that much moisture in the soil, but all of our other treatments are keeping much more moisture and for longer. So in those winter storms, mulch and a small amount of compost, much more effective. Are you giving me a time check, Erin? No? Okay, I just saw your, I saw your camera.
No, you're good. We just got a question, so we'll wait till the end to respond.
Great, thank you. And we saw, so this last element that I'm talking about with the moisture, and I'm really talking about rain a lot because it's really important in controlling these ecosystems, is what when there are not very frequent rains, we see that are on the long term, although those little applications and just the mulch can keep more moisture in that we see in this first box here, on the long term, that thick application of compost can really keep it in and retain it in the soil for a long time. So the next, so I'm going to go a little bit quicker through the nutrient cycling aspect of it. We found that those amendments were able to increase microbial activity, a really important part of nutrient cycling. Compost increases it. A high application of compost, however, actually reduced that activity, which is counterintuitive. And mulch took a longer time to sort of get going. And we can see this in these graphs. So these are two graphs from August 2018 to August 2019, a year apart. So in this left graph, we can see that mulch compared to control is on the far side, and then we have mulch. They're about the same. This arrow here is showing us that those treatments aren't very different. But then we can see that when you're adding 3 centimeters of compost, you're getting a much higher microbial respiration, and that 6 centimeters is actually decreasing it. You see less than that 3 centimeters. Not super significant, but it is still there. And then a year later, we see the same trend that more compost rather, is not better for respiration, but we see that the mulch has actually really increased soil respiration and is pulling ahead. So over time, mulch is really effective. And the nitrogen fluxes that we looked at, so not just the microbes themselves, but how much nitrogen they're making available. We saw that low amounts of compost were able to increase those fluxes, while high amounts decreased them. Mulch only slightly improved them, and confusingly, seeding improved them. So we'll go into that a little bit later. This graph is just sort of showing that we have a sort of increase as you're increasing the amount of amendments that we're using. And over here on the far right, that thick application of compost is actually reducing the amount of available nitrogen compared to all our other treatments. So that final ecosystem process that we're trying to improve is soil stability. So we took a measurement of soil stability at 2 different times in this experiment, and we found that they weren't very different from year 1 to year 2. They're almost the same, but we did find that compared to control, compared to nothing, the mulch and the low application of compost kind of decreased the stability of the soil. I'm not quite sure how to explain that yet. Hopefully more analyses will reveal that, but it's really counterintuitive that we're seeing a lot of other processes being improved, but soil stability isn't really jumping up in the same way as some of those other properties that we measured are. And vegetation, the result of increasing or changing all of those ecosystem properties and processes was that we saw a really marked increase in the mulch plots. So after only 4 months, we were able to see here in this tan color, mulch plots are really pulling ahead of all of the other amendments, the low application of compost, the high application of compost, and control. So you see more plants, and you also see the plants that are around are covering more area. So they're bigger plants, they're healthier. So more plants, bigger plants are around. After a year, so after 14 months, we see that exact same trend. So there's still a year later, there's more vegetation in those mulch plots than in any of those compost plots or in controls. These are really encouraging results, and we can see them here. So after 14 months, if you're looking on the left, you're seeing mulch in year 1 in July in the summer, really hot. And then on the right, we're seeing in August, a year later, also in the summer, a huge growth of vegetation compared to the surrounding area. And especially when you compare that to a control block, these are pictures that were taken on the same days in a control plot. On the left was in year 1 in July, there's not really anything growing there. And in August, similarly, no vegetation. So this is really just visually showing that. Over here on the right, you see a huge increase in vegetation in those mulch plots compared to the other plots that we tried. So both the small and the large amounts of compost. So to summarize all of these findings, I have this little chart here that I think is really helpful to visualize it. So we talked about on the top, we have our soil ecosystem properties. So hydrology, that's cycling of water, available nutrient cycling, which is the available nitrogen and the microbial activity that we measured, soil stability, which we measured through those aggregates, and vegetation, that we looked at them, we counted them, we measured how many there were. And then here on the left axis, we have our different treatments. So we have a control with just a few seeds broadcasted, and we can see that that was that confusing result that I talked about. It increased nitrogen a little bit, even though it didn't increase the amount of vegetation or the microbial activity or the hydrology. So that didn't improve other things that we measured, but it did increase the amount of available nitrogen a little bit. Not super significant, but intriguing. Mulch, on the other hand, which is kind of the star of the show here, really increased that soil moisture in some really interesting ways in different seasons, but was really effective at increasing the amount and also the duration of time that moisture stuck around. It also increased the available nitrogen for plants and the microbial activity, so those communities that are cycling that nitrogen and keeping it around. Didn't increase soil stability, it actually kind of decreased it a little bit, which was strange, but you can really see that here, these 3 pluses, really great with vegetation. So you compare that to the 2 compost treatments, and you can see that they have similar processes that are affecting hydrology, nutrient cycling, soil stability, vegetation, but they're just not improving them as much. So that low application of compost is not improving the vegetation like we're seeing the mulch improve it. It is, however, improving the microbial activity, the available nitrogen and the soil moisture. And that really thick amount of compost, although it is improving it slightly, it isn't very impressive. So it's improving the soil moisture a little bit, not really in the ways that we want necessarily. The available nutrients and the microbial activity similarly not doing what we wanted. And the vegetation is really going counter to our expectations, decreasing the amount of vegetation. So that is what we found, and our next steps are to continue sort of analyzing the abundance of results that we found in this study to try to answer some of those questions that I'm still really curious about. So why that seeding increased nitrogen fluxes, why that thick amount of compost reduced vegetation, why mulch had such an impressive vegetation response. I really want to dig into some of those questions a little bit more. And I also want to trial in bigger ways, more exciting ways, which we're already doing. So our lab is trialing mulch on acre-sized plots near Picacho Peak and trying it in different landscapes, positions, and in different soils, different times of the year. So to really try to figure out how we can effectively use this mulch in drylands across the world. So acknowledgements, I would not be able to do this research without my advisors, Joseph Blankenship and Elise Cornish, and my lab manager, Samuel Rathke. And I would also really like to offer a heartfelt thank you to Walter Lane, who is the landowner who allowed us to set up on his land, and all of the other people who contributed to this research. This is not just a one-person show. It takes a lot of people to do research like this, and I'm deeply thankful to all these folks. So with that, I would love to answer any questions. Thank you so much. This is my email address if y'all want to get in touch about my research or about food security in Tucson in general, especially during these times of pandemic. I would really love to connect with y'all. So hit me up. This is my email. And thank you very much. Some references and a closing slide.
Thank you, Ariel. We do have questions for you, so I'm just going to do them as they, in their order that they came in. So would you first address, did you consider using biosolids, the treated wastewater sludge, as an amendment?
Thanks, great question. So biosolids is one of the amendments that's been trialed fairly extensively here. It has been shown to be effective in certain ways and effective in others. I'm not going to dig into that research. We didn't use those amendments right now for a couple of reasons. One is that there's quite a bit of stigma around them still, because that sewage sludge, what is it? It's poop, and there's no sort of two ways about it. It has been proven to not be super detrimental, But another reason that we didn't use it in this particular study is because those sewage sludge amendments are really high in nitrogen. And really high nitrogen amendments aren't doing what we want in rangelands. So the plants that we're trying to get to come back in these rangelands are adapted to really nutrient poor conditions. So increasing the amount of nitrogen, not necessarily our number one goal. Increasing the cycling of it, absolutely. But we have found that by adding high nitrogen amendments, especially in areas like the Altar Valley that already have a presence of invasive grasses, that it's those invasives that really take advantage of that nitrogen and dominate. So sewage sludge, although it is abundant and it's cheap and it's here, is not the most appropriate for our ecosystem. But great question.
All right, sorry, I'm keeping myself muted so nothing in the background interferes. Our next question, and they continue to come in. So what was the steady state of soil, say 200-300 years ago? Mostly grass, or did it vary from decade to decade? And that's from John.
Great question, John. Historical conditions are really interesting. And the way that we observe things or know things about conditions 200 years ago are also really interesting. So one of the ways that people sort of investigate the state of soil and things is by looking at cut banks or by looking at historical pictures of areas and looking at buried areas, places where there was a layer of soil but that got buried. So there's a lot of different ways to sort of investigate with different levels of precision what the soil properties were like 200 years ago. That being said, limited time travel abilities, if you will. But we know that from the historical pictures of the above ground vegetation, the area tended to be much more dominated by grasses than by mesquites. Pardon me. So we see from pictures that have been taken over the past at least 100 years, 100 and change, that the mesquites tended to be concentrated in riparian areas. But as cattle moved in and helped disperse those seeds of mesquite and other woody shrubs, and there was less vegetation around to carry fire, those disturbance regimes led to a dominance or a propensity of shrubs and trees to sort of dominate over these landscapes. In terms of those effects on soil, I don't really know all that much about it, and I'm not familiar with the research looking into those soil properties from 200 years ago and thinking about a steady state. We know that sedimentation is a constant process, but we also know that based on areas of the grasslands right now, that there are much less intense sediment fluxes from those grasslands than from shrub-dominated ecosystems, especially during the monsoon season with those large rain events. So if we're thinking about a steady state 200 years ago, we can assume that the soil stability probably would have been better. This is all an inferential. There would be less sediment transport. Yeah, and that's all I really feel comfortable saying from my standpoint, but that's a great question, John. Feel free to get in touch if you want to talk about it later.
And our next question from Clinton, any idea how fire cycles differ, and then compost as mulch rather than dug in, as a question? I know those are two questions, yeah.
A two-part question, great. So if I'm understanding your question, Clifford, you're asking in the first part, how have fire cycles changed over the years? And I talked a little bit about that during my answer to John's question, but when there isn't enough vegetation around, like a density of vegetation close together, an amount of fuel on the ground, fire doesn't travel through the landscape as easily. And when we see mesquites and shrubs and bare ground, sort of that stable state that I was talking about before, not the grassland, there tends to be a lower density of vegetation and that fire doesn't carry. So where the grassland ecosystem is dominated by fire regimes every 5 to 15 years. You'll see a fire come through, burn some grasslands, kill some mesquite seedlings, make some nitrogen, some nutrients rather available, open up these spots for different plants to come in. So that'll happen recurrently every 5 to 15 years or so. When you have that alternate stable state of trees and shrubs, that fire regime doesn't really happen. We have a hard time getting fire to go through the landscape. So it becomes less frequent. It doesn't never happen. Obviously, there are times when it can, but it gets stretched out. And the second part of your question was about digging in amendments. So what's the difference in between digging them in or not digging them in?
And compost in particular as mulch.
Compost in particular, yeah. So in agricultural settings, when we have the ability to till in, that can be really great. In a lot of rangelands, like the one that I studied, the ability to till compost in isn't really a thing. So the landscape is extremely rocky. There are also sometimes permitting issues, like archaeological issues that you have to work out before you can bring in machinery and till. A lot of the machinery that can till is not developed to run on a rangeland and would damage the machinery really well. So the practicality of tilling in compost, rangelands really aren't where it's at for that. But it's a great question for places where we can till it in. And here yeah, I could dig into that research and talk to you a lot more about that, but I don't think that this is necessarily the time to explore that. I'll try to get to another question, but if you want to get at me, I'm more than happy to help answer more specific questions or recommendations you have about should I till in my compost or leave it on the surface of the soil, things like that.
All right, and this is from another John. How can we encourage native grasses while discouraging invasive species like buffalo grass?
Great question, other John. Buffalo grass is tricky. And I think I talked a little bit about it in some of the other questions, but to sort of synthesize, those invasive grasses like buffalo grasses, or rather non-native grasses, tend to thrive on nitrogen. So if we're adding amendments that are high in nitrogen, not a great way to discourage buffalo grass from showing up. I think that that's where mulch, sort of the rough-hewn mesquite mulch that we use, which is really just branches laid straight on the surface of the soil, really shines because it encourages the growth of natives. We didn't see a huge amount of non-natives growing or non-invasives growing in our plots. We saw no buffalo grass around. And I think that the way that you approach restoration to encourage or discourage those species depends a lot on whether they're present already or whether there's a seed source already. So if you have buffalo grass on the landscape and seeds already and they're there, it's much more difficult to encourage native grasses and discourage those buffalo grasses than if you just have a sort of degraded landscape where the buffalo grass isn't there yet. I would recommend vastly different strategies in those two contexts. Yeah, and the best one to use is once again dependent on a multitude of factors, but I think it's enough to say that you want to not add, in terms of amendments, don't add nitrogen-rich amendments if you're trying to discourage invasive species, and think really carefully about whether there are buffalo grass already present or if there aren't, when thinking about how to approach restoration. And once again, get at me if you want to talk more about it, get some recommendations about a specific site that you're thinking of.
All right, they keep pouring in. So this is from Mary Ann. What gives mulch its superior thermal and hydrologic buffer? Is it porosity? You know, the space, particle space between the layers.
Great question. So I think that one thing that I didn't illuminate as well during my talk was that compost is, when it dries out, tends to be hydrophobic. So it doesn't like to let moisture suck in and here sink in. I have some slides that can show that. So here, this is a great slide to answer that question. So here we see another hydrograph where you see those precipitation events are leading to peaks in moisture. And if we zoom in on the left side of this graph, we can see, so in blue is the compost, in, I guess that's yellow, I'm a little bit colorblind, but in yellow is the control and the orange is the mulch. So we can see that this is early in the monsoon season. Everything was really dry. Those first, if you look at the distance in between the peak of the compost and the peak of the mulch, you can see that it kind of gets smaller over time. So as that compost gets wetter and stays wetter, it can sort of allow more infiltration of water in. But when you compare that to those mulch peaks, they're way up there every time. It's not hydrophobic. It's allowing the water to go straight in to infiltrate as it would, and it reduces the evaporation. So it's shading that area, and it's also reducing those surface wind speeds. So really creating a microclimate where evaporation is reduced, and it's still allowing the maximum possible amount of water into the soil. Whereas the compost, although it is making a solid barrier and holding whatever moisture gets in there for a long time, it's not allowing those sort of smaller precipitation events to really make it into the soil rapidly. And when it dries out, it takes a while to really be able to accept more moisture. That was a great question. Thanks, Mary.
There's another great question. This is from Cecilia. Did you measure microbial activity in the compost, and might that activity compete with the underlying activity in the soil?
Great question. So we did several trials. All right, let me take a step back. I'll talk a little bit about how we measured microbial activity, and I'm gonna just switch back to this thank you for joining us slide while I do, because I don't have a helpful visual to explain this. But we measured the ability of a microbial community to degrade carbon. So we did that by taking a little soil sample and feeding it all the carbon it needs and measuring how much it respired. So how much of that carbon does it eat, does it make it through? So we measured that in the soil underneath all of our treatments. And we did see that the low application of compost increased that microbial activity. I actually might have a good slide for this. Nitrogen fluxes, bear with me for a second. This is a great question and I want to try to answer it really well. Okay, so this might be the one. The graphs are a little bit small, but these are respiration measurements that we took at different times in the year over the course of this experiment. Yeah, so you can see that in the top left in February, the mulch and compost, so these are measurements taken in the soil, they're almost the same. In the thick, heavy layer of compost, so up here on the far right, you see a slight reduction. So is it because there's more microbial activity in the compost itself and they're competing with nitrogen lower down? It's possible, we don't have a way to exclude that, but I think it has more to do with the amount of moisture that's making it into the soil in February, because we know that compost doesn't accept that moisture during those small precipitation events. When we compare that to May over here, which is the next sort of one over microbial respiration SIR May, you can see that that heavy amount of compost is increasing the microbial respiration way more than the other ones. Once again, the moisture is there now, so it's no longer a limiting factor. And also any nitrogen that was around in that compost or any microbial communities that were there are sort of sinking into that soil, and really with the dissolved nitrogen and carbon and any other nutrient into that soil, and really able to let that microbial community flourish. So I know that these weren't directly your questions about did we measure in compost and soil, which we did a few times, but it's not really helping us answer sort of the question that we're getting at, or that we're trying to answer with that microbial respiration, which is within the soil, how well are those microbial communities able to degrade carbon? How much of it can they eat? And we saw that adding compost when water is available allows those microbial communities to really flourish and make it through more carbon than when we don't add compost. Kind of roundabout way to answer that question, but I hope that that sort of gets at what you were driving at there.
All right, I just wanted to tell you we did have two thank yous. Stella, thank you for a great presentation. We still have a few more questions too, but I also wanted to let you know that Walter from Peru was in with us on this session. The other question I want to pose, and this is from Hal, can cattle be used effectively as an alternative to fire to maintain landscapes, and what are the upsides, downsides of that approach?
Ooh, great question. Now we're going from soil science more into rangeland management and fire fire ecosystem dynamics. Really fascinating areas of study. Ones that I'm a little bit less well versed in, but still have looked into less as a master's student and more as somebody who's an ecological restorationist and really interested in these things. And I think that in certain ways, cattle can serve a similar role to fire. And in certain ways, they can't. And there are also consequences of having large mammals on this landscape that are not present when you're using fire or when fire is in the landscape as a disturbance element. You can, so the way that fire is maintaining the grassland as a disturbance element is that it's going through and it can kill small mesquite seedlings. So that's something that it does really well. When cattle are out on the landscape, they aren't doing that as well. Although they'll sometimes eat the mesquites, the young ones, which is good, they're also eating mesquite pods and bringing those pods all over the landscape. So although they're taking down some of those grasses and allowing maybe new grasses to sprout and opening up some ecological niches for some other plants, they're also doing a great job of dispersing mesquite seeds. And when those mesquite seeds germinate and take in those grasslands, they can sort of start to lead a transition towards an ecosystem that's not dominated by grasses, but by mesquites. I think that the answer is that you sort of need both, truthfully, and you need to time them well and know where your cattle have been if you can, I guess. I don't know. This is really less of my expertise in knowing how to move cattle on the landscape. But I do know that they help propagate mesquites and that they're not killing the seedlings in the same way as fire is, because once those mesquites get a few years old, the cattle are less likely to go after them because they have big spines on them when they're seedlings, or even if they do, they can resprout really well, whereas fire will take them out more effectively. Yeah, do I think that cattle cannot be used to effectively manage a landscape? Of course not. But I do think that you need to bring in that fire regularly if we're talking about large scale land management like the way we're doing it. I think that it's an intrinsic part of this landscape, and I don't think that cattle can entirely replace it. If you take fire out, you're gonna have to mimic that disturbance in other ways, and cattle just don't cut it.
Okay, I've got another question from Richard. Why doesn't mesquite mulch, which is a legume, add a lot of nitrogen to the soil?
Great question. So it adds some nitrogen, not a lot. And one of the reasons for that is that mesquite, they're legumes, they're nitrogen fixers. That nitrogen lives in the roots, in the nodules that they form with their symbiotic bacteria. So that is where sort of the storage of nitrogen is it's in the soil, it's in their roots, it's in those nodules with the plants. When they need it, they take up that nitrogen, they use it in the tree to grow new wood, to send out new leaves, and there is some nitrogen in those leaves. So, but that sort of process of growing new leaves, bringing nitrogen up, there's some losses there. So already you have a little bit less nitrogen there than you do necessarily in those nodules themselves in the soil. And then when you clip those branches and bring them somewhere else, if they're green and there are leaves on them, that's great. There's nitrogen in those leaves. Those leaves will fall to the soil, but those leaves are exposed to the elements. And one of the reasons that nitrogen is such a limiting nutrient in our ecosystems, and in any ecosystem really, is because it's extremely volatile. So our air is made up of 70% nitrogen. That nitrogen is diatomic nitrogen. It's bound together with these really solid bonds. When it's fixed by the legumes, it becomes biologically available. And when it's in those leaves, it's also biologically available. But what that means is when those leaves then make it onto the ground, they get broken down by sunlight, they dry up, microbes eat them right at the surface to build their bodies, and there's just a lot of losses. And the wood itself, what sticks around for a long time in the mulch, not very nitrogen rich. So it's the answer to your question, why doesn't it add a lot of nitrogen? That nitrogen that is in the mesquite leaves or branches, in the mesquite mulch is in the leaves. It's very labile. which means that it's very easy to volatilize, to get out there, to go off with the wind or get eaten by microbes or termites or something else. So it doesn't have a chance to really make it in the soil in the quantities that it does when it's in compost or something like that, or other amendments that can sink in better.
I have another question, and you know, we're getting a little close on time, so maybe one or two more questions, and then we'll encourage folks. You can put your email address back up because they just can have some very in-depth, great questions for you. But
Yeah.
what effect does pumping the aquifer have on all of this?
What effect does pumping the aquifer have on all of this? Great question. And now we're going into hydrology, another one of my hobby interests, but not making it into the thesis. So to answer that question, let's start on a landscape scale. So let's broaden out from my little 3x2 meter plots and really look at the Altar Valley as a whole. If the water table is high enough there, there'll be places where the water table meets the surface of the water. And that's when you get springs or when you get perennial rivers. So you'll have surface water. When you pump that water table drops low enough that that water isn't making it out to become surface water. Great. We still have water, however, maybe really close to the soil. And if it's within the root zone of some of those grasses, they can help grasses grow. Usually, even when the aquifer is really high in these areas, it's nowhere near close to those grass root zones. So the aquifer doesn't have any effect on necessarily those grasses, but not a direct one rather. But if it's not coming out as surface water, wherever that water gets to the surface, grasses that are there, shallow rooted plants, can take advantage of that. So the groundwater pumping will have an effect on the riparian areas or on the floodplains of those riparian areas if the channels aren't too deeply incised. So if we draw water too much down and there's no surface water from those springs specifically, we're gonna negatively impact the presence of grasses and other shallow rooted species here. Mesquites are amazing plants. They are not like grasses. They can send tap roots down for, 30, 40, 50 meter, like extremely deep. We found mesquite roots going way down there. And if they can access the groundwater there, they can keep growing. If you theoretically had an area where the mesquites could access that water, but the grasses couldn't, the mesquites would be really flourishing. Keep pumping that water. Maybe the mesquites don't have access to that groundwater anymore. They won't be as big. They won't be the giant mesquites we see in some of our riparian areas. But they're still going to survive. They're not going to die just because they don't have access to that groundwater. So it won't kill off the mesquites. They'll still stay there. They'll be smaller, but mesquites can do just fine with all their shallow roots accessing the same sort of water that is available to those grasses. So pumping that aquifer is not going to negatively impact those mesquites in a way that'll necessarily bring back a balance towards grasslands. So to sort of wrap it all up together, we're too far gone now, but if we could get that aquifer back up, and in certain areas, I think we can raise the level of that water table to get more surface water, that would help grasses return to the landscape, especially big riparian grasses like sacotones that are disappearing all over our landscapes. And if we can get that water to flood up onto the floodplain, that would be amazing ecologically.
We're kind of wearing you out, but I'm going to pose one last question, and then I'm going to encourage folks, because there's some great questions here. Please, feel free to contact Ariel using his email address. And I see we have a Boyce Thompson Arboretum contact that's, a possible partner or, collaborator with you. But the last question, standard compost is acidic. What effects does that have on native plants and soil stability?
Great question. Yes, compost is acidic. The soils that we were looking at were also slightly acidic, maybe less than compost, certainly less than the compost that we were using. But in general, the soil has, especially for the amounts of compost we're using, an almost inexhaustible buffering capacity is what they talk about in terms of pH. So although in that compost itself, you will have maybe a more acidic environment, it's not going to make it very far down rather. That soil pH is really difficult to change, especially long term. In our study specifically, we can sort of think of the effects of mulch in a hierarchical way. Before we worry about the effects of pH on plants, we're going to worry about their effect sort of smothering native grass seeds, for example, which is something that was important in our study. A lot of the grasses that germinated in the mulch were not seeded species. They were ones that were there already. And we saw very few of those species within the mulch. So we're going to be worrying about that first. We're also going to be worrying about the amount of water. So we're going to worry about that second before we worry about the effects on the pH. So those are things that we want to look at first. Then maybe on par with that pH, we're going to be looking at sort of the biological activity, which is also going to influence the acidity of the soil potentially. And that gets really complicated, so I'm not going to go down that rabbit hole. I think that one of the interesting ways that an acidic soil is going to affect those nutrient cycles, if we go back to the ecosystem processes, is it'll make different nutrients available to plants that maybe aren't in less acidic environments. So in this environment, it's already slightly acidic, might not have a huge effect, but in somewhere where you have like a pH of 8.1 or something like that, a really basic soil, and you add a really acidic compost, maybe something that's more around like 5 or 6 or something like that, you might be able to mobilize some nutrients, especially right on that soil compost interface that wouldn't otherwise be available. That might be available to your plants and increase the sort of health of those plants there. Another thing that pH does is it can change the nutrient and sort of chemical soil structural dynamics in the soil. That's another huge rabbit hole that I'm not going to go down here. I wouldn't worry about that as much. I think that the biology, eating that carbon in the compost and exuding different microbial products that kind of glue the soil together is going to be more important than any sort of acidifying effects that would break that soil apart. Super interesting question, and a really fun one to think about, sort of, as you can kind of see from my answer, from a bunch of different angles. But if we're sort of like coming back to the beginning and thinking about how is it going to influence plant health or plant dynamics, I wouldn't worry too much about that pH. I think that there are other things that it will be doing positively and negatively to plants before we have to be thinking too hard about what the pH is going to do.
Well, Ariel, you're getting a lot of thank yous in the chat section for an absolutely outstanding presentation. And I want to thank you for your time and wish you much luck on your master's defense. Very exciting, your thesis defense. We also hope to retain you in our community as a wonderful researcher and community member. And I just want to remind everyone, I mean, we have Ariel's email. He's already welcomed everyone. If they would like to interact more and learn more from him, you're free to email him. And if you would just flash the screen that shows the College of Science website, where you can see our next talk next week. It'll wrap up this 3-part series. And again, these talks are from different themed series at different venues, but we're going to wrap things up with the science of aging. So you do register for each of these talks and visit the College of Science website there to register like you did for this event. And I thought that was fantastic. Thank you for your time. And I think we'll close the session. And again, it'll be uploaded, also available. The link will be made available on the College of Science website, how to get to our YouTube channel. So this talk, last week's talk, as well as the final talk next week will also be uploaded. And there are many talks from former Science Cafes there too. So without further ado, have a great evening and continue the great work.
Thank you everyone.
All right, take care. Have a great evening all.
Bye now.
Take care.